Our third example of how to find the efficiency of a heat engine is a slightly different approach here. Here we're given the power output of this engine and the efficiency, and they're asking you to find the rate at which heat is extracted from the hot reservoir and the rate at which heat is dumped into the cold reservoir. So the way to do that is to simply divide each of these three here by time, because if we go the change of the hot reservoir, or the rate at which the temperature, let me say that again, the rate at which heat is extracted from the hot reservoir per unit time, and you make this the dW dt, the rate at which work is done per unit time, and you divide this by time, and you say the rate at which energy or heat is dumped into the cold reservoir per unit time. So all I did was simply divide each of these three quantities by time. Then you realize that this is equal to power. Power is simply the rate of doing work per time. And so if we then put this quantity in here, we should be able to figure out these quantities the same way we did before when we didn't have everything divided by time. However, units of horsepower are not standard units, so let's convert that into watts. And if we convert that, we have to use a conversion factor. Watts at the top, horsepower on the bottom. 1 horsepower is 746 watts. So the first thing we want to do is convert that into watts. 240, now be careful, don't confuse the unit watts with the W for work. So 240 times 746 is equal to 179,040 watts, which is 179,040 joules per second. All right. So now that we've converted that, we can come up with our efficiency equation. Efficiency is equal to work over Q hot. And so what this then means is we can say Q hot is equal to work divided by efficiency. And then if we divide everything by time, we can divide the left side by time. So we can say the rate at which heat is extracted from the hot reservoir per unit time is equal to the rate at which we do work per unit time divided by the efficiency. Now we can go ahead and say this is equal to 179,040 joules per second divided by the efficiency of 28%, which is 0.28. So divide this by 0.28, and we get the heat extracted per unit time from the hot reservoir is therefore equal to 639,429 joules per second. Now obviously we don't need that many significant figures, but let's not worry about that. Second part is we want to know how much heat we dump into the hot reservoir, and of course, in the cold reservoir. And we can say, well, the delta Q delta T to the cold reservoir is equal to the amount of heat that we extract from the hot reservoir minus the amount of work that we do per unit time. And so what we can do there is we say, okay, that's equal to the 639,429 joules per second minus the work done per unit time, which is 179,040 joules per second. And so the difference between those two, so minus 179,040 equals, and so round it off, well, first we'll write 460,389 joules per second. So of course we want to round that off to maybe 3 significant figures, because 3 or 2. So this can be written as 6.4 times 10 to the 5th joules per second, and this can be written as 4.6 times 10 to the 5th joules per second. And that's probably a more appropriate way of writing the answers with the correct number of significant figures. But notice, just like we had Q, W, and Q, we can have delta Q dt, delta W dt, and delta Q dt here, and you work the problem out exactly the same way. So, example 3, and I think now you're ready to solve all those efficiency problems.